Okay, so good afternoon everyone. I'll be speaking on a particular topic that's building an iOS jailbreak from scratch. I'm Umang Raghuvanshi. I'm 20. I'm a computer security researcher. I primarily work on coding and process automation. I occasionally release some of it.
Hey, it's Cooper. So this talk was being live streamed, which was a bit of a surprise for the audio people. And you could tell that the first bit of the audio that you just heard was essentially the room audio being picked up by the microphones again. The audio engineers immediately went to work trying to fix this, but it takes them up until about the 4:30 mark before they manage to get it working. So you may want to skip ahead to that.
In my opinion, 6 is the right ratio. Again, this is, I'd say, a hyper-simplified view of the iOS kernel. You've got the open source components, which are Mark, BSD, and the IOKit framework itself, and the closed source components, which are the proprietary kernel extensions. So the XNU kernel is a hybrid kernel. It incorporates the Mark microkernel, which was released by Carnegie Mellon University, and wraps it with BSD APIs. Some parts of it are released as open source software by Apple. The device drivers themselves are often written as part of the iOS framework, and most of them are closed source. An interesting paradigm shift here is that quite a few device drivers have either moved to or will be moving to DriverKit, which is essentially ARKit but in user space. So that narrows down an attack surface a bit more, but I think that we're getting ahead of ourselves. So let's take a step behind. Like previously discussed, why would we like to target the iOS kernel? For one, it's significantly more complex than a boot chain and it has vast attack surface, like absolutely huge. The closed source kernel extensions, in my opinion, do not get the attention that they deserve when being audited for security issues. And if we compromise the iOS kernel, we should be able to execute code in EL1, that is in the ARM exception level 1 or ring 0 for my x86 friends out there. This also means that we have control over all user space processes, which from an attacker's point of view is interesting. But there are reasons to not attack the iOS kernel too. The open source portion of the XNU kernel is heavily audited. This doesn't mean that you cannot find bugs in the open source part, but I find it more productive to have a look at the closed source kernel extensions before performing a source code audit of the open source parts. Also interesting is that some of the attack surface is simply inaccessible from inside the sandbox. So attackers either need to find something accessible from the sandbox. This is something a lot of other people are also working on, so that again is heavily audited, or they must find a way to escape the sandbox and then attack the kernel. Also, some parts of the hardware, such as the hardware crypto engine, are inaccessible when you attack the iOS kernel. For example, like Nikias must have said that the AES engine is only accessible from high boot and below. You cannot access this after the device has completed booting. You cannot access the GID keys, which are used to encrypt quite a few interesting things. One also noteworthy thing is that the iOS kernel has a significant amount of vulnerability churn. This means that a lot of people are looking into it, a lot of people are finding bugs, and a lot of the bugs are getting patched. Well, that is just a fact of life, I guess. So let's attack the iOS kernel with the means of a kernel exploit. For the purposes of this talk, I generalize a kernel exploit to be any piece of code that gives me two functions. One of them is read kernel memory, which will take an address and the amount of memory to read and return back the memory it read from the kernel's address space. Its complement is write kernel memory, which given an address will write to it inside the kernel's address space with controlled contents. Now, the way most kernel exploits do it is to craft a task code that corresponds to the kernel task, which is the kernel process that's running itself. What, in effect, this allows you to do is to have full code control over the kernel's process. Why? For that, we'll have to have a very brief detour into mark ports. I promise to make it quick. But a mark port, generally speaking, is, say, a container, or rather, postbox. If you have a send write to a mark port, you can send the postbox letters, and if you have a receive write, you can receive letters from the postbox. There's also an option to have a send once write, which allows you to send a letter exactly one time. Now, tasks, which are the mark representation of processes that are running, each of them have their own task port. And this task port is special because if you have the ability to send a message to this task port, you can control the task completely. You can read and write inside its address space. You can create new threads in that task. And you can, like I said, control it for what it's worth. Assuming that you had a task port to the kernel task itself, you had a send write to it, you could either read or write memory by calling mark VM read or mark VM write on that port. But this isn't as straightforward as it sounds, because in order to craft this very task port, the ability to read kernel memory is a prerequisite, because there are certain values that need to be read from the kernel memory. For example, the kernel's IPC space, the kernel's map, or the kernel task itself, before we can craft a task port and acquire send write to it in order to read and write kernel memory. This is kind of a chicken and egg problem, which we'll explore shortly. So let's talk about a really nice kernel exploit that came out Hi, Brandon is at for Project Zero. We released OOB timestamp, which is a semi-controlled out-of-bounds write in the kernel heap. Interestingly, Brandon himself could be here presenting at Nullcon, but unfortunately he couldn't make it. And while this wasn't a part of my talk, I decided to add it in at the last moment to give the talk some much needed context. Now, a function called the EGX command queues process kernel segment command performs an out of bounds write to the kernel heap with control data, semi control data. In fact, we cannot control what's written, but we can have some approximation of what is written. And interesting to note here, EGX command Q is a proprietary kernel extension. We do not have the source code for that extension released by Apple to the public domain. Like I said, if you were to order the closed source key the way Brandon did, I'm sure that there are several interesting things just waiting to be discovered. Let's see how it works in a very, very high level overview, because going into the depths of it and the intrinsics of it would take quite a lot of time. So OV timestamp in general sends a mark message and never receives it. This mark message has out of line ports, port send writes. By using this controlled out of bounds write to free some of these ports and reallocating them by string data, we can in effect have control over the contents of a mark port inside kernel memory. Once we are done modifying the mark port, we simply receive the message containing the drafted mark port and use it to read and write kernel memory. But given the fact that we only have control over a mark port and we do not have all the information we need in order to craft a fake passport for the kernel task, how do we read kernel memory? Well, that's a really interesting question, and the answer is PID for task. As unintuitive it sounds, normal circumstances, if you had a send write to the port for a particular task and you call PID for task, you would get the 32-bit process identifier for the task. And it's a very obvious question. How do we turn this into a way to read kernel memory? For that, we'll have to look into how it's implemented inside the kernel. This is quite a bit to go to, so let's break it down a bit. First up, we have 4 key pieces of function that we'll investigate one after the other. First thing the function does is converts the port name to which we send the message into the representation of the task inside the kernel. Once that's done, it gets the process structure corresponding to the task. After getting the process structure, it gets the process identifier from the process structure. And lastly, it copies out the process identifier to the user space where we can read it. Now, given this information, we can abuse PID for task as a controlled 4-byte read given control over contents of a mark port and get an 8-byte read. For example, we can just combine 4 adjacent 4-byte reads together. In practice, this would be enough to craft a task code that would behave exactly like the kernel's task code, as we can now read the contents of the kernel map, the IPC space kernel, and the value of the kernel task, all of which are required in order to craft the fake task code we want, which is required in order to read and write kernel memory in a stable way. But there's one small problem. We still don't know where these values are located in kernel memory due to a technique called, or rather a mitigation called KSLA, or kernel address space layout randomization. Now, Castler slides the kernel's virtual memory mapping by a random amount every boot. This random amount is generated by a previous stage in the boot chain, usually iBoot, and it does that by getting some entropy, taking an SHA-1 hash of them, and then selecting a byte from this entropy, multiplying it by a constant, and sliding, that is linearly moving the contents of the kernel by that amount. In order to defeat kernel address space layout randomization, in effect, we must know at least one pointer that's inside the kernel text mapping, that is inside the kernel code, the virtual memory mapping of the kernel. We currently do not have that, but fortunately for us, OOP timestamp gives us a pointer to the IPC space, which is a structure in kernel memory that holds the various ports that we have back to our process. We can use this address to the address of a mark port, which in effect points to an IO surface. What this allows us to do given the fact that we can now read from the values of an iOS surface, is to read the virtual table, the virtual method table from inside the iOS surface, which itself is stored in the IP key object field inside the task port, and if we have the address of the variable, we know for a fact that it points inside the mapping of the code. We can then move downwards. We can search for the Markov header file message, which is a magic value that signifies the start of the kernel. And in effect, we can repeat kernel displays their randomization. But why are we doing this? Because using fit for task to read kernel memory is very inefficient. So we'd like to craft a real task code. More importantly, the actual problem here is that we cannot write to kernel memory using this technique. So we move on to craft an actual task code. Remember, we are now able to read all the values that we require in order to create a fake code that behaves exactly like the kernel's task code. And if we gain task write to this craft code, send write to it, we can both read and write memory in the kernel's address space by using the mark API, specifically the mark read or mark write. Implementing this, we now have control over the kernel memory, and the next logical step, I believe, is to escalate our privileges a bit and to become the user. That itself is simple. We can find the structure that represents our processor memory, and we can perform a few writes. We can change a UID to 0 or GID to 0, and you would think that that should be enough to allow us to do whatever we want, right? The sad answer is no. This is because our application is running in the container sandbox profile, so we cannot perform several interesting observations because they are explicitly blocked by sandbox. So importantly, there's a lot of syscalls that we like to perform in order to build a jailbreak, such as execve or fourth of which are blocked by the sandbox. Let's research into how this blocking itself is implemented and how we can circumvent it by having a look at the open source portions of the iOS kernel. The first step is in kernel4.c, where we can see that function is called which checks something inside a process structure, and in case it returns an error, we cannot fork at all. We follow the cross-reference into the Mac process check fork, which is part of the mandatory access control framework. This itself calls another function using the CR label, which is stored inside the struct ucred, a structure which contains the user credential information for our process. Specifically, it uses the CR label in order to determine which sandbox we are running. By extension, what exactly are we allowed to do? The MAC of the Mandatory Access Control Framework is in fact the very foundation of the iOS sandbox, and by using the CR label value, it determines operations that we are allowed to perform in the current sandbox context. For example, an application running inside the container sandbox will not be able to access files outside its container. It will not be able to write to them. It will also not be able to spawn new processes or perform privileged operations. The question is, how do we defeat this? Because remember, we are currently running as a normal app inside the container sandbox, but with privileges. There's a couple of ideas. We could change the label to a null pointer, which would allow us to bypass some of the MAC checks, or we could do something more interesting. We could read the kernel's struct ucred, which contains its own CR label, and change our ucred to the one of the kernel. This itself bypasses most sandbox checks because it's obvious the kernel is allowed to do whatever it wants because it cannot enforce its own permissions. That's something for another execution level or something that's not taken care of at all. Implementing it is rather simple. It's barely 3 lines of code. We find the kernel process and read the pointer to the ucred structure inside it. We then leak the amount of references of the ucred structure so that when we exit a process, the ucred itself doesn't get freed and lead to a kernel panel. Then we change our ucred with that of the kernel. Sounds perfect, right? In theory, this would allow us to do whatever we want to do without having to face any sandbox fix because, as we just discovered, the kernel itself is not subject to sandbox in a way that user space applications. However, there is a problem. As soon as we try to do anything useful, we get this. The kernel itself panics with an almost cryptic panic message, shenanigans. It's almost as if the person who wrote that code is somehow telling us that, hey, don't do those shenanigans. Let's look into what that is. First up, we look for cross references to the string shenanigans inside the kernel binary, and we find one fitting in a rather obvious place. Now, the code itself is a bit complicated, so let's break this down a bit. First thing the code does is checks if the kernel's UCRID is being used. It then checks if the UCRID is being used, whether the process that's using it is a kernel process. And if it's not, well, you read that block here and panic. All of this is done inside SB evaluate, which is a function that evaluates the sandbox policies. I think that this mitigation is a great idea, but it's a terrible implementation. Why? Because the value of the kernel's UCRID is cached. What this means is that we could write to kernel memory, we could corrupt the pointer that contains the kernel's UCRID, and in effect, we could pass this time check every time we want to use it, because it would compare our UCRID, which is in fact the kernel's UCRID, to a corrupted pointer. That check would obviously never pass. Moving on, we'd like to remount the root file system. Why? Because the Apple file system partition, which is currently mounted on the root partition, is mounted as read-only. And we'd like to write some files. We'd like to write some files outside of a container, but we can either write them in /private/var, which will lead to a few problems with the sandbox because you really aren't supposed to execute binaries from there, or we could write it in the root file system itself. Now, I personally prefer to write it in root, so I'd like to remount file system. Let's see how we can do it. We can. Kernel explicitly allows you to remount the root file system as /. This is done by checking a flag inside the enode that represents root directory, and if the mount rootfs flag is set, the mount operation will simply be denied. How do we work around this? Well, an idea would be to patch away the check in the function that verifies it, but that is wrong. And here's why. On the Apple E10 SoC and later, the memory management unit simply prevents writes to protected memory pages. And these protected memory pages include everything from the kernel code, the EX code, and all the constant regions. So it basically prevents you from writing anything that's not supposed to be writable. In effect, what this does is that it makes patching the kernel's code non-trivial. It makes it very hard, and we have to restrict ourselves to only modifying data, which is the read-write mappings of the kernel memory. We cannot modify the kernel's code. We cannot modify the kernel's constants either. So how do we remount it?